In this lecture, we use the formulas that we derived in a previous lecture video for the least squares estimators of the beta parameters to fit a simple linear regression model to data with a quadratic trend. Here are the data. We have 10 observations, and in a previous lecture, we created a scatter plot to investigate the relationship between y and x, and we saw that there is in fact a quadratic trend relating the response variable y to the explanatory variable x. Now, from that example, recall that we need to regress y against x squared rather than against x. And so that we can express this model in canonical form, we're going to create a new variable. We'll call it w, and we'll set w equal to x squared. So w is a derived variable. Let's go ahead and add this derived variable to the data set. And so here we have it. We see that, for example, 0.2 squared is equal to 0.04, 0.3 squared is 0.09, and so forth. The next thing we need to do is to calculate summary statistics that are needed for the formulas. Now notice that these are the same summary statistics that were used in fitting this model using the normal equations. And that makes sense because the formulas were derived from the normal equations themselves. So the sample size is 10. The sum of the w values, which is the same as the sum of the squared x values, is 3.84. The sum of the squared w values, which is the same as the sum of the x to the fourth values, is 2.5332. The sum of the response variable y is 44.74, and the sum of the products of the w and y values, which is the same as the sum of the product of the squared x values with the y values, is 22.6249. Now that we have these basic summary statistics, we can calculate what we might call the intermediate summary statistics that will allow us to calculate beta 1 hat very easily. And the first of these is the corrected sum of products of the w's and the y's. Now remember, we are regressing y against w, and so that's why this quantity is called s sub wy instead of s sub xy. And so s sub wy, which again is the corrected sum of products of the w's and the y's, turns out to be 5.44474. Next, we calculate the corrected sum of squares of the w values, and plugging in the summary statistics needed for this, we see that this is equal to 1.05864. Okay, now that we have s sub wy and s sub ww, we can calculate beta 1 hat very easily because it's just the ratio of these two values. And so beta 1 hat is equal to s sub wy divided by s sub ww, and that turns out to be 5.143145,923. Once we have beta 1 hat, we can calculate beta 0 hat using this formula. So beta 0 hat is equal to the mean of the response variable y minus beta 1 hat times the mean of the variable that we're regressing against, and that is w here. So minus beta 1 hat times w bar. And since we have summary statistics calculated in terms of the sums rather than the means, we can express this formula equivalently as shown here. So beta 0 hat is equal to 1 over n times the sum of the y's minus beta 1 hat times 1 over n times the sum of the w's. And when we plug in the summary statistics here, we get beta 0 hat equal to 2.499,031,966. And so expressed in terms of the derived variable w, the least squares estimate of the simple linear regression function is given by y hat equal to beta 0 hat plus beta 1 hat times w, or as we see here, 2.499,031,966 plus 5.143,145,923 times w. Now, obviously, in a real-world example or real-world situation, we would round these estimates to whatever's appropriate for the particular situation, but I'm showing full precision here just so you can see if you get the same values as well. Now, corresponding to this estimated regression line, which is in canonical form, we have a plot here of a scatter plot of the data and the least squares line superimposed over the data, where we have y on the vertical axis and w on the horizontal axis. And so you can see here that when we express the model in canonical form, so y equal to beta 0 plus beta 1 times w plus epsilon, we see that the deterministic part of the model, beta 0 plus beta 1 times w, is linear in w. And so that's why this scatter plot and the least squares line are linear in this particular plot. But let's see what happens when we express the model in terms of x. And so expressed in terms of x, the least squares estimate of the simple linear regression function is y hat equal to beta 0 hat plus beta 1 hat times x squared. And so we plug in the values for beta 0 hat and beta 1 hat into this expression. And so you see here that this is the least squares estimate of the simple linear regression function when it's expressed in terms of x. Now, the plot of this function and the scatter plot of the corresponding data has on the horizontal axis x instead of w, or equivalently, we have x here on the horizontal axis instead of x squared. And so when we represent the graph this way, then we see that we do have that quadratic trend because, again, with this representation, the deterministic part of the model, beta 0 plus beta 1 times x squared, is not linear in x, it's quadratic in x. All right, and so again, this is why we see that quadratic trend in the data. And you can see that in the same way that the canonical, or the model in canonical form was fit very nicely, the model fit in terms of x is fit very nicely as well. All right, they're equivalent fits. Both of these models have the same value for SSE, the sum of squared errors. Now, recall the values of the least squares estimators that were obtained by applying Gaussian elimination with Jordan reduction to the augmented matrix corresponding to the normal equations. And so in a previous lecture video, when we fit this model before, all right, we set up the normal equations, we created the augmented matrix corresponding to those normal equations, and then we performed a Gaussian elimination with Jordan reduction on that augmented matrix to come up with an equivalent matrix that's easier to solve, and that transformed matrix, which is in reduced row echelon form, is shown here on the right on this slide. And so when we did this previously, we saw that the least squares estimator, beta 0 hat, was 2.499,031,966, and beta 1 hat was equal to 5.143,145,923. And those are the same values that we got using the formulas. So the values of the least squares estimators obtained using the formulas are the same as those obtained by solving the normal equations directly using Gaussian elimination with Jordan reduction. So we see that we can fit a simple linear regression model in a variety of ways. We have seen examples where we fit a model visually. We have used Gaussian elimination with Jordan reduction to solve the normal equations for the least squares estimators. And we've also used the formulas that we derived from the normal equations to calculate the least squares estimators directly. So that's what I wanted to show you in this lecture video, and I would encourage you as you go through the course, as we do examples, and as you work problems, to try solving these problems, try fitting these regression models using both techniques. So I'll see you in the next lecture video.